to Physical Science in the AM. I'm Joel Shaduk, and it's a beautiful day out there. Hot dog, it's going to be out of sight. Hot day. Anyways, we're taking up these questions. Locate the center and focal point. I've given you the image and the object. So, one of the rules, the object that I'm looking at, is that first rule I find the easiest. If it hits the mirror when it was going parallel to the principal axis. Oh, well, I'm undo that because I want to phone. This means grab it. If it hits the principal axis, it goes through the focal point, but we know that it lines up at the edge of the image, right? I'm going to use that rule to find the focal point. So that's working. And this must be the focal point. I put a big F. Okay. And the other rule that I like that finds the center, the only rule that goes to the center, is if something goes through the center, it comes back on the center. But it also lines up with the tip of the image. So this must be the center. Okay, so there, located the center in the focal. Two rules. No need to use all three. This is obviously a virtual image because it's behind the mirror. You know it's behind the mirror because the object's on one side of the mirror in between the image and the object. Okay, so this one got a little tricky. I use these rules. Actually, I'm going to pull this down for the next question. Parallel to the principal axis, hits the mirror and goes through the focal point. But in this case, you have to line it up behind the mirror with the and line that up. Oh, this makes sense because the only way to get a larger virtual image is to be between the focal point and the mirror, right? There it is. Now I'm going to give it a solid line. Because really what happens is the dotted line represents stuff that isn't actually happening. Perfect. The ray actually hits the mirror, goes through the focal, but it lines up so that you know where the image is. So I've got the focal point. Mark. Now, using rules to show where the center, I'm going to only use a dotted line first, and then I'll shade in or color in afterwards. Now, here's how I'm going to do it. I know that it's got to hit the image. But I'm just expanding that. Okay. So the actual ray is the one that goes to the mirror and bounces right back to the center. I'm going to mark my center. Okay, so we can predict focal points and centers. Right? see what the last one. Well, let's move this around. Okay. The only thing different about this is I'm going from right to left. So it's just a mirror image of diagrams we usually left to right in the air. So it's a mirror of the way we usually do. Like you can look at it here this way, or I can turn around and look at it. That's business, right? The other way around. So it's the same rules, but I'm hitting the mirror. I'm going parallel to the principal axis, hitting the mirror, and I'm lining up. Okay, that's the first rule. So there's the focal point where it crosses the principal axis. Ooh, calling this out. Okay, I labeled that wrong. I was thinking about a phone call. There we are. My mistake there. Got that? The center. Okay, it's the same rules. Sometimes when you do everything left to right, but screws something down. Right to left. Oh. Okay, there we are. So this is the old line up the tips of the two things. Hits the mirror, comes back. That will be the center. Okay, there we have it. Those three diagrams, you should be able to locate any center and focal point given an image. But the other typical question is center and focal point are given, locate the image. Or, and I did one example where we had the image locate where the object was. You can work these rules frontwards, forwards, or back. Diverging here. We've already seen them. I'll just show you one again. Big guy. There's diverging there. It looks like the size of a shoplifting or anti-shoplifting mirror. Right? And every image, doesn't matter how close or far you are, you're going to be smaller. Right? Objects in this mirror are closer than they appear. And that reminds you that's a side view mirror. They're not quite as bubbly. Actually, sometimes on really big trucks, you ever see a real bubbly side view mirror? They're usually a second, they have their flatter mirror, and then they have this bubble. Right? So, and that's because in a big truck, your visibility is way up. So, we've looked at these before. We're going to just pause for a second. So these are always virtual images. Use the rules for curved mirrors, locate the image, then list its characteristics. Okay. I can already list the characteristics every time we said. Characteristics, size is smaller. It's always going to be erect, never inverted. Therefore, it's always going to be vertical. And I could do that before, as long as I know it's divergent. I'm going to just actually copy that. Paste it down. I'll leave it there. It's a diverging mirror. That's the way it's got to work. So we're going to try the rules, and these rules, because they're virtual images, we're definitely going to use dotted lines behind here. And you'll notice that our focal point and center behind the mirror. It's a virtual focal. Always going to have dotted lines. Now, let's go with this. I'm going to just so first rule, same rule, parallel to the principal axis, but it lines up with the virtual focal point. So I'm going to use a dotted line, and then I'll take it from there. Fill in. Oh, here's the focal. Okay. Now, like I said, I'm going to shade that in. Using the first rule. I like to use the center rule. I find with diverging mirrors, the second rule, where you line up a focal point and then it comes out uh, parallel to the principal axis, that was kind of goofy. I'll show you what I mean, but I'd have to line it up, dot, dot, dot. I'm not going to use this, but I'm just doing this. It really means that this happens, and then I go parallel to the principal axis. Wait a second. I would have had to have been dot, 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 this, and that's where it intersects. That's the end. Okay? Just disappeared. But anyways, I'm not going to use that rule. I find that one confusing to a lot of students. So I'm going to use the rule where we line things up with the center. So I go to the center, draw a dotted line, and then shade it. So this really is a rule where so if something lined up with the center hits the mirror and bounces straight back on itself. Right? Same line. But we get a crisscross. This is where your image is going to fall. Smaller, erect, and virtual, as predicted. Your image is always going to form in that close region. Like I said, the second rule, I'll just read off. Somehow, something good. I'm going to try, once again, to say, if I want to use the second rule, I don't like it, I line up first with the focal point. And then I say, bang, hits the mirror, and then it goes parallel, and then gets there. We're predicting the same image, but I find that one confusing to use because you have more dotted lines. So I don't recommend it. You can. You'll do the same thing, but when it's farther away, it just means it's smaller. The exact same rules. So first I'll start with parallel to the principal axis. Going to go through the virtual. All right. And I'll shade in the side on the real side of the mirror. There we go. Then the center rule. Shade in. Anything on the mirror side. And the center rule is perfect. You know that means it's the mirror back. So you see where the crisscross is? Damn, it is really that makes sense. Okay, so it's the same thing, you just get it super small. So diverging mirrors, there's really no variations. It's just even smaller. So then you have a space. Common uses of a diverging mirror. And we've mentioned these already, but side view car mirror, right? For your I'll just jump side mirror, right hand side. I gotta put R H for right hand screen. Just to clarify, right? Warning you left doesn't have that warning, so don't believe it is. As close as it looks. And then the security mirrors for shoplifting, etc. There's other reasons. Oh, roads, like people have mentioned around corners and stuff like that, to avoid a collision. Now, illustrate the advantage. I did the drawing ahead of time just because it takes long. I'm slow, so I'm going to remove this box. The advantage is you can view a wide angle. If I have a flat mirror, a plane mirror, you see how it reflects every way. Diverging mirror, got a large, wide angle. And pause the video. In case you're just joining us, this is physical science in the AM. Talking to the recording. Well, we're going to flip the page, and we're going to join. I've started the recording again, and this is physical science in the AM. Once again, third time. So we're going to do these things by drawing, which we've done. We've exhausted all the possibilities. Now the mirror equation and the magnification equation. You probably recognize the magnification equation after 2 out of 3 parts. We use the same one for the camera, pinhole camera, right? The only thing added in here is M for magnification. Now, with this formula, you can take any 2 of the 3 chunks and make it an equation. Don't try to use all 3 at the same time. So I can either say magnification is equal to HI over HO. I can say pi ho is equal to negative di dou. Or I could go magnification is equal to negative di over dl, depending on what you want. This is sort of like the way the law of sines, if you're familiar with that, some of you, you know how you're given 3 chunks for that. You choose any 2 of the 3. If you never heard of it, don't worry. You'll learn to do by doing it. Now this equation, though, algebra for this involves reciprocals, because every variable is on the bottom, bottom. That means you got to do your arithmetic with a calculator. I'm not expecting you to add fractions. You can do that in math, honestly, which I highly recommend if I teach math. But here we're just doing it with a calculator. So when you put 1/3 plus 1/5, just put it in your calculator. Every fraction can be thought of as division in business. Okay? So 1 divide 5 plus 1 divide 3 is 1/3 plus 1/5. But they didn't go story, but still, it's the same answer. Get a decimal for it and then figure out your variable. More about that as we do that. Okay? Now, an overview. I'm going to give you those 2 sets of equations on any evaluation item. But not to know a few things about this. DO, distance to the object, it's always positive if it's a real object. I put down negative for virtual objects, but we're not going to have virtual objects. But in theory. So it's always positive. DI, distance to the image, is positive if it's a real image. So if it's on the same side of the mirror as the object. And you know real images can be solved with candles, right? Negative for virtual images. That means it's behind the mirror. And we've drawn those. If it's negative, you also know that it's direct. Therefore, okay. Focal, the distance to the focal point, focal length, is positive. It's a converging mirror because it's in front of the mirror. Negative for diverging mirror because it's behind the mirror. We always use dotted lines to locate. And negative height, we're familiar with this from the pinhole camera, means the object or the image is inverted. A negative magnification. If I just said -2, it doesn't mean it's smaller. It's actually 2. It's twice as big, but it's upside down. It's inverted. So negatives just mean for heights or magnification. It just means it's inverted. Okay? Read it. Learn to do by doing. So, let's do it. A candle is placed 15 centimeters from the vertex of the converging mirror. The other name for converging mirror is called, have a sketch, just because sometimes if you're a visual person, you need to just have an approximate sketch. Maybe you don't, but I have a focal length of 10. And it's a positive because it's in front of you. Calculate the location of the image. That's the key. Don't worry about magnification. One over F equals 1 over DI plus 1 over DO. I know I'm going to use this because it has DI and now the information. DO and F. Well, let's throw some numbers in. 1 over F. Well, that becomes, read carefully, candle is placed 15 centimeters from the vertex of a converging mirror. That's the placement of the object. So this is the focal length, 10 centimeters. That's my F, and it is a positive 10 centimeters because it's a real focal length of a converging mirror. Let me put the 10. I normally put in units, but I know a lot of you skip them until the last set. Actually, that's what gets nasty. So I sometimes do. We're looking for DI. This is the image location here. DO is 15. Now, if you've done pre-calc 20, or you take some rational functions, rational equations. Not so sure. I know in workplace you don't really work with things like this. Foundations, I forget. Do you? Work with equations? I don't think so. Okay. So this is kind of new to you, algebra 1. But it is and it isn't. We have to get DI alone, but don't get it alone in one step. You can't just flip everything. So I have to subtract 1 over 15 from both sides. So that's the next thing I'm doing. I'll keep DI on the right-hand side. 1 over 10. I'm going to drop the centimeters. Minus 1 over 15. I'm keeping the 15.0 and the 10.0 because it reminds me, my final answer, I'm going to have 3 significant digits. I told you I'm going to use a calculator. We're going to use the calculator too. I'm going to pause the video while I bring up my cup. I'll start recording. As I mentioned, every fraction is a potential division problem. So I'm going to go with, I want a decimal. 1 divided by 10, subtract 1 divided by 15. I'm going to hit it and get a decimal. Now, right now, I'm going to keep more than, actually, you have a calculator that brings up the previous answer. Don't wipe out your thing. I'm going to write down those as 0.03333. I know that I'm going to round to 3 digits now. Okay. 0, 1, 0. I'm going to have a few. It goes on and on and on. This is what you have at this set. Now, depends on nifty with numbers. To solve this, you could multiply both sides by di, and divide both sides by 103. Okay, I put a 0 there, but divide by the 333, and it'll be 1 divided by 333. I'm just explaining what I do, but I'll write it down once. If you're good with numbers, though, you can just jump straight in. Then it turns into these guys trade places. So I'm going to write down di equals 1 over 0.0. I put a lot. You could type that into it. Or a lot of people have an x minus 1 button. What does -1 mean as an exponent again? Like seconds to the -1? Remember, it just means 1 over. If you hit on my calculator, my exponent, oh, I hit this, it takes my answer to this and flips the reciprocal. I don't know on the small calculators. I see your button is right above the 7. If you have that button, use it. If you don't, manually type in 1 over. Okay? Now, you get a nice number of 30. If you have to manually type, then just type in 1 divided by 0, 1, 0, 3, 3, 3, 3, 3, 3, 3, 3. But you have it 1 over it. But you have to have a number in it. Right? Put a lot of 3s in them. So di is equal to 30. How do you do that? 30.0 centimeters. That's 30 on the nose. Okay? If you can't find the button, do 1 divided. Is that what the x to the minus 1 or 1 over x? Either way. If you want to, your last answer should never have a that, but yes. Yes. So I was just asked if you wanted to use just a bar over this and cut it off there, you can. Like, I know what you mean. Because you know what you mean. But final answers should always be rounded to the right number of significant digits, not the decimal place. Okay. Now I'm going to just, there's more parts to this problem, but di is 30. Listen to the image. This makes sense. Let's just go back and think about this. Oh, yeah. I'm getting a positive distance to the image because this should be a real image, and it should be in front of the mirror because it's converging mirror, concave mirror, and it's in front of the focal point. Welcome to Physical Science in the AM. Joining us in progress. Anyway. So I'm going to take a look at the B magnification. This part of the equation is pretty easy. Then, I look at this and I think, di-ho or di-do? Which information do I have? I have the negative di, negative sign built into the equation. The di over the do. So I'm going to write that down from this formula. I'm using this portion. Okay. I'm going to solve for magnification. Negative sign's built into the formula. My di, I just figured it out, 30. I'm putting down centimeters here, because you got to make sure that they're in the same units, and they are. My 15 is my do, and that was from the given. You can use the calculator if you wish, but I don't need to go 30 divided by 15. Okay, what this means is it's negative, so that means it's inverted, therefore it's real, and it's twice as big. We saw situations like that with the candle. This is now calculating exactly what you would expect from those with that formula. C, the height of the image. Now, I have two choices. I could use hi ho equals negative di-do, di-o. Or, it's a little easier to just go with the magnification part. So I'm going to go with this. It's the same amount. So, hi ho. I have negative 2 for the magnification. I'm going to replace that answer. This formula. Height of the image. The object is 3.5 centimeters high. The object is 3.5 centimeters. Now, you know intuitively it's twice as big for me. But they won't always be this simple. Okay. Algebraically, to solve this, we multiply 3.5 to both sides. It cancels on the right-hand side. We've got 2. I'll write it down. I'm 3.5. Okay, so we got 7. Now, I'm only keeping 2 digits on this because my 3.5 centimeters, pretty sure, yeah, only 2 digits. Okay, we solved ABC, all the parts. Right? So, because I made a mistake, thank you. I arbitrarily just, yeah, I do that when I talk. Thank you for calling me out right away. Didn't mean to wait. Okay, height of the image, negative because it's inverted. 7, twice as big. Okay, diverging mirror example. Same equations, but with this, let's take a look. Diverging mirror with a focal length of 15 centimeters used. Right away, when I see a focal length, flip back to the page, I'll do it for a second. We see, oh, right, focal length is positive, converging mirror, negative, or diverging mirrors, even if I report it as 15. Sometimes I will write down focal length of minus 15, I'll put that in there. Don't double negative if it's a diverging mirror. Okay? So, focal length is negative 15. It produces an image 7.5 centimeters away from the mirror. That's the DI. Now, image is 7.5 centimeters away from the mirror. Which side of the mirror is it on? Behind the mirror or in front of the mirror? Diverging. Okay, we'll flip back and figure this out. The eye is positive for real images, but negative for virtual images. It means it's behind the mirror. Now, a diverging mirror, always behind the mirror, always virtual. Okay? You kind of have to know that. Like I said, though, if it was somehow given as negative 7.5 right away, don't double negative. The DI is negative 7.5. Okay? Picked up on that? Where is the object? DO. That's what we're looking for. I'm going to put in the formula here and we'll sub it. Okay? Don't need to help. So, 1 over f is 1 over negative 15. Over DO, that's what we're looking for, is the DO. 1 over DI is 1 over negative. I'm going to use a calculator, of course. Cut it up. I'm going to go with 1 over, I'm going to drop the centimeters. They all match. Subtract negative 1 over 7.5. We know what subtracting a negative. You can think of it as adding to if you want. I'm strictly doing this because you can enter it in the calculator. But you can use plus. Addition. Okay, we're going to get a decimal number. You do yours, I'll do mine. Double check. 1 divide negative sign 15. Subtract 1 divide negative 7 point. I'm doing it. It's good because I get a positive. And I want Joe to be positive. It's always okay. I'm going to write that down with a lot of repeats. Positive 0.0666. I'm not going to erase this off my calculator though, because I'm going to use that x minus 1 button. It's like so just going to press it. Oh, press the wrong one. And I get 15. And I go 15.0. Okay. What's the magnification? M is equal to negative di over do. That. Now my di was negative built into the formula, but then I'm going to use my negative 7.5 centimeters. My do I just found. This makes sense. It's a smaller object, and it's negative. It's positive. It's direct, and it's virtual. So I'm going to use 1/2, but I'm going to put it as a decimal. You know what? I made a mistake earlier with significant digits. Here's my mistake. Or do you guys see it? My DO, or, yeah, my DO answer. What's my mistake? Should be. No, it's 1 over 15 is 0.066. That isn't it. It's that I have 15.0. Now, it's not a huge deal, calculation-wise, but I don't know this that accurately because I don't have two digits, 7.5 going in with that measurement. 15.0, the negative 15.0 for focal point. You always go, that has three digits, but you always go to your least amount of significant digits. That's, I'm not marking for significant digits at this point, but I will be, so I'm modeling what you need to. And I'm making mistakes too. Thank you, all right. I feel much better. Just a ray of sunshine in this gloomy world. If the image is 1 centimeter high, what's, okay, anyways, M equals, I got to get this done. Hi-ho. So I'm going to put in my my 0.5. HI, I'm giving the image this time. Find the height of the object. In this case, think of this as multiplying both sides by HO, dividing both sides by 0.5. It's really just switching spots, right? I'll write that down. I'll make some space here. Do I have these always one chunk? No, I don't. Here's what I'll do. I'm going to just do the old follow my pen. So I'm going to do the work that should be underneath there, rendered on the screen, as HO equals 1 centimeter divided by half, which 1 divided by half is 2. There we go.